Yeah, before Niranjan.
Yeah.
Nothing. Or Niranjan?
Good morning.
Fine. Yeah. Okay. I haven't posted this yet, but we will have a homework 9 during a week. So the midterm coming up. One week from Friday is the midterm. Midterm will cover everything that we do until the day of the midterm, but having said that, concentrate on stuff after midterm one that's expected, but at the same time, technically it covers everything from the start of the semester. It's built on that in a sense. Today we will change gears and start partial differential equations. We'll stop the complex analysis exploration. One can extend that further. Whatever we started on with analytic continuation, we can do it gamma function, zeta function, and so on, beta function, and so on. But I think somewhere I wanted to stop and do something else. So we will start with the main idea I would like to convey in this whole discussion is the idea of Green's function and two interpretations of Green's function. One will be the simple one, that is what we will mostly use. That's what most of the times we come across, is the idea of Green's function as a way to solve inhomogeneous differential equation. If we have right side not equal to 0, Green's function is a way of solving it. But there is also a deeper interpretation of Green's function where it is a way of accommodating fluctuations. Whenever we have especially quantum fluctuations, then Green's function is an automatic candidate for that. So in that sense, it is very physical. But the way most of the time we will be doing will be solving partial differential equations. But it is the same Green's function that gets into, if you were to quantize the system in any way, it will be the same Green's function that comes into picture. So I'll emphasize that wherever it comes. But let's begin with the simple, at least motivate what Green's function is. So Green's function, just a motivation, and very quickly I'll get into doing a partial differential equation with a particular example. What do we understand by a Green's function? Anyone? What comes to your mind? Electric potential, something more? You want to add any electric potential is not Green's function, right? But we are thinking roughly in that along that line, let's say. So what do you mean is, let's explore that. So usually we have our Maxwell's equation as epsilon naught times electric field. Let's say we are in vacuum, and there is a position dependence here. I'm not writing that, and there is a charge density on the right side. That's correct. That's electric field, and this is charge density. Give me the charge density. This differential equation, if you solve it, gives you the electric field. We often like to do it as a second differential equation. So electric field is also equal. It's a position dependent quantity, not necessarily constant. It is equal to negative gradient of a potential, electric potential, or already introduced. Is this always correct? What is wrong in this? It's only if it is electrostatic. Like most of the time in the beginning of the electromagnetic course, we are doing statics. So in general, there is a time dependent part also to this. Magnetic potential, electric potential. If it is time independent, this is not there. So if, so this is equal to 0 if the curl of the electric field is equal to 0, which is the next, which is the other Maxwell's equation. Right? So if this is equal to 0, then that's equal to 0, then electric field is negative gradient of phi. So it's not always true. So in that case, you have negative gradient square of epsilon naught times phi, which is a position dependent quantity. We have killed the time dependence there. That's equal to rho of r. And here I say, so that's your electric potential, but that's not Green's function. This is not Green's function, but there is a Green's function associated in this context. What is it? Usually you come across Green's function in this context for the first time, probably, whenever you're doing. But if I were to say, I want to find out what is electric Green's function in the context of electrostatics, what would it be? So the basic idea is, so remember how you do this in electrostatics. You have a charge density. Charge density is built out of point charges, right? You add up all point charges to get a charge density. Right? This is nothing but you have a lot of point charges. You would say, oh, that's not discrete. If it's not discrete, make it an integer. A charge density involves a lot of point charges. Pick one point charge out of it. So make it a point charge. So then you have a square epsilon naught. But now, the moment I say it is a point charge, I have to say I have a choice of keeping it wherever I want to. Like here, the whole space is filled with the charge density. If I'm picking one point charge out of it, I have to specify where. And that will be R prime. Let me put it on the other side. So a point charge is L cube R minus R prime, right? That's the charge density for a point charge. It exists only at one point. So it's a delta function. And on the right side, whatever you have is what you call a Green's function. Let's give it some units. So let's say, let's keep it like this. This is Green's function R, and now it depends on the position of R prime. Let's say R prime. So in this sense, maybe I should put, no, I don't want that Q over epsilon. So if if you were to identify So G of R, just to make the correct identification, if I were to write this as epsilon naught over Q, because there's a point charge here, right? I can keep, and then make this a potential or a point charge. So the idea is that the potential for a point charge is what Green's function is. So if you have a right hand side completely spread out, you have an arbitrary function. Build this function out of delta functions. Add up all these point charges, which is what we say as superposition principle, right? If you have charges, you can add up all the electric field simultaneously. That's basically the idea of superposition. So if I have this, I can add up to get my solution. But what is electric potential due to point charge? 1 over, correct? So this is epsilon naught over Q. So this is Q over 4 pi epsilon naught times 1 over R or R minus R prime, right? If it is at origin, it is 1 over R. If it is not at the origin, you will say this is R minus R prime. And Q is just so that because we wrote this slightly differently as a the way we wrote it is not an electric potential. Q cancels out, epsilon cancels out, so it is 1 over 4 pi times R times R prime. This is the Green's function. Green's function for this differential equation. So let me motivate this further. Again, whenever you want to think of a Green's function, think of a point charge. The electric potential due to a point charge. Once you have a point charge, you can do this anything. You can basically add up all the point charges, and that gives you the complete solution. That's the same idea. You're interested in the function, partial differential equation for an arbitrary function, for an arbitrary source. You do it for a point source instead. That's called the Green's function. And then the solution can be written in terms of the Green's function. So what is the solution in terms of this? How would you do that? If I know the Green's function, this you usually know, right? This is the first thing we learn, that is a Coulomb's law, right? So what is the electric potential for a distribution of charges? If I have 1 point charge, what is the electric potential due to a 3 point charge? You do superposition, right? You add up. So how do I add up for this? So that is the solution. So phi R, phi of R. I have to add up all these things. That's equal. Think of discrete first. So you would do Q over 4 pi epsilon, right? So this is Qi over 4 pi epsilon naught times R minus R prime summed over I. That's the superposition principle. But we are having a continuous distribution. How does this generalize? This becomes, instead of summation, this is an integral. You integrate, here you're summing over I, here you integrate over R prime. So that's E cube R prime. And instead of summing over charges, you have R prime here and 4 pi epsilon naught or R prime. Right. This is in the physical context, right? If I know the point charge, this is how you would build it. But if you're doing partial differential equations, you may not have this physical interpretation. You want to do it in the Green's function. So how do you write this in terms of Green's function? This whole thing is Green's function. 4 pi is Green's function. So this will be equal to, that is a epsilon naught you pull outside, EQ prime, and the Green's function R comma R prime times charge in state. So again, summarizing. So this is the problem, like in electrostatics. Problem is R or epsilon naught, right? That's Q. Oh, this is 1 over epsilon naught rho of R. That's your solution you're trying to solve. Instead, you do construct a Green's function, right? That was my nephew trying to connect. I think he accidentally connected. Yeah. Okay. Hopefully he understands. Yeah. Okay. Construct a Green's function. Construct Green's function. Notice what do you do? Start from here. Instead of the complete potential, you're talking about the potential due to a charge at a point. And that is, you introduce a Q. Oh, no, we did not introduce a Q, right? Yeah. So that's a matter of scaling. And we did not introduce epsilon either. So again, this is the equation we want to solve, but we construct a new problem where the right-hand side is only having a delta function. That's called the Green's function. Once that is there, the solution, so solve for it. Once you have that, so solution will be, if you can solve for this Green's function, phi would be, that will be equal to, in this case, there is an epsilon naught coming in. So this is dq prime, d prime times over epsilon naught. Notice, solve this equation and just sum over all the point charges. So again, the way we are motivating this is that solution for a point charge, which is basically a delta function. Point charge is a context-related point. In electrostatics, we say it's a point charge. In a general differential equation, it's just a delta function. It may not have that meaning of a point charge, but some point source. Instead of saying a point charge, we have to think of a point source. And most of the time, we will be interested in solving it in one-dimensional problems, and we will be basically working out the details of how this goes through for specific problems. Is that clear? Any questions here? And we'll talk about the details in here, how we'll construct, how we go from one step to the other. But that's basically the motivation. So we need a partial differential equation. Start from here, preferably equal to 0. Then we'll put a source, and then we will say how we can do this for a delta function. There are specific nomenclature for this. There is a particular solution. There are independent solutions. All those are technical terms that we use in this context. We will come to that wherever it is applicable. So we should have a specific differential equation we want to work with. we will mostly work with one-dimensional case just so that it is easier. This is a complete three-dimensional problem, so let's leave that alone. But of course, this will be the context, like always, even if it's a three-dimensional problem, we will say that this is a planar charge or a spherical charge. We will always convert it into one dimension. So whenever we say there is a lot of symmetry, what we are basically doing is converting the problem into a one-dimensional problem. But that will be our goal in a sense, our overall theme, like the way we said in complex analysis, Cauchy's theorem, everything runs around that. In physics in general, elementary physics, we do say Newton's law is the central piece. So this will be our central theme, sort of, and we will build different equations on it. Any questions on that? You should ask me if you have any interpretation of. Very simple, but that's what it is. Except when it comes to quantum mechanics. In quantum mechanics, this will have a meaning, like there is a physical meaning given to the Green function. Here, this is just a mathematical construct. It has no significance as such. Even without a Green's function, you can live that. But when you go to quantum fluctuations, then this has a meaning. And I'll hint on to that a little bit as we proceed, but not at this point. Okay, so let's start slowly. Have simple equations. Let's do. I think it is harmonic oscillator. That's what it's called. Harmonic oscillator is position dependent or time dependent? It's position dependent. So what if it is time dependent? What do you call it? Huh? Non-harmonic? No. Let's say you have something oscillate, okay, at a certain frequency. Yeah, it is called the harmonic oscillator. It is called harmonic. Yeah. Like harmonic. So let's model this. Let's say that. Let's go all the way back to Newtonian physics. So this is a frictionless plane. Let's make it horizontal ground so that mg and normal force cancel each other. So then we have a spring, and that's here. Let's say that's x equal to 0. X equal to 0. What are the forces acting on this? That is mg acting downwards. That is normal force acting upwards. And if it was at equilibrium, it is at x equal to 0. If I were to stretch this, so somewhere around here, there is an additional force, and that is opposite to the direction of the stretch. If I stretch the spring, then it tries to pull inwards, it tries to compress. If I try to compress the spring, it tries to stretch out, right? So the force is kx minus kx. So in the horizontal direction, so we say in the y direction, so this is your x, that's your y. In the y direction, there is no motion, so few lines. So Newton's law tells us that mass times acceleration is equal to mg plus the normal force plus the force due to the friction, force due to the spring. So that's the force due to the spring. or vector. So that's Newton's law, right? Motion of the mass n is equal to the vector sum of all the forces acting on it. Take the y component of this equation in the y direction. There is no acceleration. It is not flying off, so it is 0. That's equal to minus mg plus n plus 0. So this implies that n is equal to mg. There is no friction, so non-revolutionary doesn't have any role in this problem. In the x direction, that's what we are interested in. We have mass times acceleration in the x direction, and there is no mg component, so that's 0. Normal force 0. Force due to the spring is minus times kx. That's your equation of motion if you want. Acceleration is second derivative of x, position as a function of time, and that's equal to minus kx. Here x is a function of time. There is a mass on the left, there is a spring constant, right? K I didn't define here, right? So K is the spring constant. I think in the recent books in the last 30 years, if you look at it, everyone uses K, so there is no confusion. But if you go further back, 50 years and 100 years back, probably the notations might be. There is a K on the right, there is an M on the left. These are all given quantities. We can all absorb this into a single variable. So it is convenient to divide this out and define K over M as a single quantity. So let's have omega 0 square, omega 0 on the subscript, meaning that it is not going to change. It is a property of a system. What is the dimension of omega now? Radians? Frequency, yeah. So if if you look at here, x cancels out, there is a 1 over times square, so we should have the dimension of frequency. So this is, so we have a differential equation now. E squared x t, that's equal to omega squared and x of t. That's one of the first differential equations, or one of the first few differential equations you see. You must have seen this again and again. You must have run it much more than this, but let's begin with. We would like to write this equation as, put everything on the left hand side and think of this as omega naught squared minus x of t is equal to 0. When you write it like that, you sort of see, if I were to think of my electrostatics problem, if the right hand side was 0, what is my electric potential? It's either a background or it doesn't exist. If you don't have a charge, it doesn't create any potential. But it can, if you put in boundaries, it can satisfy solutions. You often talk about, what if I put two metallic conductors, no charges, still you talk about electric potential in between two plates. Right? Similarly, here also, we will talk about, even though there is no right hand side, we will have solutions here. So electric potential can have solutions even when there is no charge. But what we are mostly interested in is that what happens when you put in a charge. So we are now going to put in a source on the right side. So this is very simple. This is an oscillatory motion. We will do the solution in a few minutes. And we will also put in friction and do more on it. But what we'll be mostly interested in is that we don't want this. We want to actually have a source. So we want to say f of t. I want to pull and push on it, right? This is a forcing. So this is a forcing. Like, it's called forced oscillator. instead of a simple harmonic oscillator oscillating on its own, if I were to make it oscillate, or for that matter, do it in, it doesn't have to be with a particular frequency, I can do it with any function. Give me any arbitrary function, I should be able to do that. And how does it change now? So I'm going to change this equation accordingly. So this is now forced harmonic oscillator, and I'm going to come back to, I think I can go on the other side, right? Forced harmonic oscillator, and the only difference will be a horizontal force added on to that. It is mass times acceleration would be equal to mg plus the normal force. All vectors, so all the signs are included in the vectors. There is plus the force due to the spring plus the driving, right? This is called a driving force, or it's a forced oscillator. So this is a driving force. I'm saying the driving force is in the horizontal direction. And in that case, you will say this is mass times acceleration. In the x direction, this is 0, that's 0, minus kx plus f of t. Again, divide out by the mass m. This is g squared x over dt squared. That's equal to minus k over m x plus f of t over m. This is nothing but our frequency. Plus omega naught squared times x of t. That's equal to f of t over m. Now, this is an equation that we just constructed. It is convenient, or just to stick with some notation. I think in my notes, I usually put in a minus sign always. So it's convenient to put that minus sign on both sides. So this will be your source. This is a homogeneous differential equation. And this is an inhomogeneous differential equation. And our goal will be to solve for this inhomogeneous differential equation when the homogeneous differential equations are available to us. If we know the solutions for this, can we find out the solutions for an arbitrary source, not just a particular source, for an arbitrary source? And that will be the idea of a Green's function. So first, go back and let's solve this differential equation, and we'll come back. So this should be elementary. So that's straightforward. But we will, while we are there, we will spend some time on it and introduce friction here and try to solve this for friction too. What are the solutions to this equation? That should be straightforward. Sine and cosine, right? So we have x of t. And how can you solve for this? What's the procedure you will use to solve for this, by the way? I mean, best is by guessing. There is usually, at least from my experience, even though when we are learning differential equations, we say that there is the separation by parts. There are some 2-3 methods we teach, but most of them are almost applicable only for very specific, very elemental situations. Most of the time, you guess on the solution. It's like integration. Elementary, already worked out problems can be done, but if you're in a new regime, you have to guess on it. So if you can satisfy this equation, you're good. So the idea is that go here and ask, think of a function whose second derivative is the function itself. Look into all your functions you come across, probably at this stage in your education. Have you guys done special functions? I will be teaching it here. Special functions. What's the most complicated function you've seen? Maybe I can have the discussion like that. List me function. How about that? Let's go by that. Tell me any function that comes to your head.
Bessel function.
Bessel function is a special function. Yeah, that's what I was hoping someone will say. So Bessel function is a special function. But what are the functions you can think of? Or yeah, you guys are all very sophisticated functions. Good, very good. So gamma function is gamma function a special function? It's an analytic function. Yeah, good point. You don't have a variable there, right? Yeah, it's not the way we classify it, it's not a special function, but yeah, good point. But I was just asking you for a function, and it is a non-elementary function. What are the elementary functions? What's the first function you studied when you were in high school? The very first function you studied?
X squared.
Huh?
X squared.
X squared. Polynomials? Yeah, okay. Polynomials. So polynomials is any function that you can write as ax plus bx squared plus bx cubed plus 1 and end it, right? So some x raised to n of alpha. You have to end it, then it becomes a polynomial. So and you can divide this so you make it a rational function, so on. So what else? Exponential, yeah, good, right? Exponential x. And then keep going. Sine, cosine, let's say, in principle, all that comes into this, right? There is an exponential and then natural log. But sine and cosine, everything can be built out of this. So you're saying sine, cosine, or trigonometric function can be built out of exponentials, right? What else? There isn't much, right? These are the elementary functions. There isn't much, right? Believe it or not, we have very limited exposure. This is very rich in a sense because we can divide polynomials through polynomials. Like we have x plus x squared divided by a cube of that. So that's very rich in that sense. That covers a lot of stuff. But just with these are called the elementary functions. Just with this, we work on almost most of engineering can be done with that. No, that requires a detailed one that requires special function. But the main challenge here is that most of the time when we are doing integrals, we cannot do the integrals. If you have seen it, differentiation can always be done, but most of the time integrals cannot be done. And when it cannot be done, what you do is that you say that's a function. Right? You just say that I'm going to work with the integral itself. So it becomes a function. For example, if it's a polynomial, same thing. If you cannot sum a polynomial, you deal with that polynomial itself. And if it's an important polynomial, for example, when you're doing gravity, which is what became very popular when Newton gave us the gravitational law, we were very interested in planetary motion. So everyone is working with that. So you find the properties of these integrals which you never solve, right? All the series polynomials you never solve. So you give it a name, but you figure out or you invent a lot of identities associated or discover a lot of identities associated with it. And those are what we call special functions, which are not really elementary in the sense that they cannot be written in terms of exponential log sine of this. So you cannot integrate and integrate them in an elementary way, but you can write that as a series and define it as a series, and you have all the identities that you need. For example, sine of x is basically a series, right? It's just that we have so many identities for sine function that it almost seems like it is elementary. We can do whatever we want with sine and cosine. The only difference between an elementary function and a special function is that we don't have enough identities. We haven't discovered enough identities associated with special function because we use it in a more niche problems. if we wait enough, maybe 100 more years, maybe we will discover a lot more identities, especially with computers around. So we learn more identities, and it makes it easier and easier to use that. So in terms of this elementary function, my point was that you can solve for this. It's cosine and sine, and it is a times cosine omega naught t plus b times sine omega naught t. There are two integral constants. Since
what about the exponential I omega naught t as a solution?
Yes, that is also a solution. Yeah, good point. Why can't I write? So is this a solution or c exponential? This is your question, right?
Yes.
Why can't I write that? Right. Good point. Yeah. Why can't I write that?
Yeah, right. E to I omega cosine, so we can
Yeah, why not write cosine? And so you're saying that, oh, I can write this as cosine and sine. So suggestion is that
change A or B.
yes, so a plus c cosine omega naught t and plus b plus I c, I suppose. Is that correct? Okay. So you can write it even if you put in exponentials, but is it okay to say that x of t has a solution of the kind, let's call it another a prime cosine omega naught t plus b prime exponential of I omega naught t. Can I mix it up? Is it okay or not okay? Often we write this without this piece, or can I write this instead? So you do say this, right? This seems to be okay. Like this is common, right? You must have seen it written like this. In fact, if you expand this out. But is it okay to work with this as a whole? So what is the guiding principle? There must be something that tells us that, oh, this is allowed, that's not allowed. Again?
Boundary conditions.
We haven't introduced any boundary conditions here. Boundary conditions will be, I think probably you're saying you're meaning it correct that whatever is the arbitrariness in all this, there seems to be that this solution is different from this. But when we put in the boundary conditions, it will take care of itself on its own. I think that's what we are trying to. That's correct. Every time we have a differential equation, we have to have boundary conditions. Without boundary conditions, the differential equation is not stated completely. You have to have an equation plus two boundary conditions if it's a second order differential equation. Like it can be an initial condition or bound. If it is x coordinate, you say it is boundary conditions. If it is time, you usually say it is initial condition, but you have to provide that. And in those terms, these gets fixed anyway, so it doesn't matter how it is. But to begin with, how do you know that it's even, for example, let's say what is not allowed, right? Right. Look for what is not allowed. Yeah, sine and cosine are too simple. Okay, but what I can say is that anytime if you want to put in two solutions, they have to be independent of each other. And then the question comes, what do I mean by independent? So independent solutions, so there must be a definition for that. Independent solutions, let's say x1 and x2 are solutions. So you define what is called a Wronskian. So W, if you have two solutions, x1 and x2, very straightforward. You have two solutions, x1t and x2. In this case, it can be cosine or exponential. That could be your two solutions. Construct a determinant in the following way. So there is x1t and x2t. And then take a derivative of the two. This is dx1 over dt dx2 dt. If this is equal to 0, so if this is equal to 0, then they are dependent. If this is not equal to 0, not equal to 0, otherwise, right? Equal to 0, otherwise, it is independent. So let's evaluate this for our case. So the Wronskian for cosine omega t, and then exponential of I omega t. So that's to be a Wronskian. Take the derivative of this, so this will be sine omega t with a negative sign, right? The sign is negative, and it is I omega naught. And this will show up actually. Yeah, there's a homework problem in which you do this when there is a harmonic oscillator. This problem, whenever you introduce the damping in it, then there is a special case when you get confused with the solution. In the over damped situation, you will, or critically damped situation, you come across this. And so you will see this in your homework also. So this is equal to okay. Both has exponential, right? So I have I omega naught cosine omega naught t e raised to I omega naught minus or plus sine omega naught t times e raised to I omega naught. That can be simplified probably. There's something wrong here, right? Dimensionally wrong. Yeah. Then I take a differentiation. There is an omega naught. Minus omega naught. So this is plus omega naught. So omega naught comes up. I can pull out the I omega naught. Then there is e raised to I omega naught t cosine omega naught t and minus I sine omega naught t. That's equal to I omega naught times e raised to I omega naught t and e raised to minus I omega naught. Oh, I'm out of the board. And that's the same as I omega naught. So it is clearly not zero. So this is an allowed solution. Cosine and exponential is an allowed solution. So you can work with it. Okay, having done that, so let's quickly do a boundary value on this so that at least no, I can do damp case also. I think at least I'll build it up. Okay, so having said that, let's work with exponential. No, let's work with cosine omega naught t plus t sine omega naught t. At this stage, I need to put in the boundary conditions. Let right. So let x of 0 be equal to. Let's consider a situation where you pull it and then you release it or keep it general, right? All the time. Probably you've done this in other courses many times. So you always take the extreme scenario where there is only position or velocity. Let's keep both, right? At x of 0, that's equal to a, and velocity at 0, right? Just x of 0. Whatever is the, this is v0 over omega. So that, dimensionally, something. What should I say? So it's just v0. Yeah. That's your initial conditions. Then you would say x of 0, which is equal to x naught, that's equal to a. Cosine of 0 is 1 and e is 0. Right? That's your first equation. And velocity at 0, I should write this down here. Velocity is minus omega naught a sine omega naught t plus omega naught t and cosine omega naught t. So put in the boundary conditions. So that's your e naught equal to that's 0 plus omega naught b. So I learned this implies that a is equal to x naught and t is equal to v naught over omega naught. So your solution is, in general, t equal to a x naught quiz. Right? Was there a quiz today? I think I remember last time I tried to do something in Mathematica. Did I try to? Oh, so did you guys try Mathematica? Could you all use Mathematica? Okay. So you have never used Mathematica? Oh, okay. Have Mathematica? Nathan?
I used it.
High school. Okay. Yeah, not here. Okay, so here's a quiz. So you want to plot like for fix your x naught. So let's say for x naught is equal to 1 and V naught over omega naught equal to 3, let's say. You want to plot this. So, yeah, crash course on mathematics. Go to the computer lab here. I'm going to construct a problem in your homework where I will make you use Mathematica, because there is this nice feature our university has started where you can get Mathematica on your computer very easily, like just by giving a website address, as far as I understand. So I'll try to give you the steps related to that.
You have to request them to send you the.
No, these days activation code, if you're inside in the campus, you just, there is a website address using your SIU login. Not even that, if you're inside the campus, you just have to give a site. I mean, there is a web server which has all your information. So you just give that address and you're done, kind of. At least it turned out very easy for me. So I think I should just ask you guys to do that in a few steps, right? That might be beneficial. I'm not saying that it is the best thing available, but from my experience, if you're doing physics and you're doing a lot of analytic stuff, it is an extremely powerful tool. It's a paid software, that's why I don't encourage it too much. If you use it somewhere here and then you leave the university, then you're stuck sort of with not having access to that. So, okay, even if the homework problem is not there, do the following. Go to the computer lab, this computer lab here on this floor, right? On any of those computer, you should be able to open Mathematica. Open Mathematica. Mathematica. I think it is, whether it's a Linux machine or a Windows machine, both will have it. If it is a Windows machine, you should look for it on the list of what is it called? Start button, I think somewhere you'll see. If it's a Linux, just type Mathematica. And so open Mathematica. And next is plot. Like, let's not plot this, let's plot a simple. So this is how you will. So when you open Mathematica, it will say this is not log, it is input. Okay. So this is input. This is how it will look like. This means input one. So you give an input and it will give you an output. So in the input, this is the syntax. So plot. So any function you want to. So capital P is important with the syntax, mathematical related syntax. Let's say sine of x, square brackets are important. So you're plotting sine of x and you have to tell where to where. Right? So you're going to say that x going from, let's say, minus, like pi is 3.14. So let's go from minus 2 pi or minus 4 pi, right? 4 into 3 is 12. So let's say about minus 15 to plus 15. Then close. Okay. That's the syntax for plotting it. And the only trick might be, or non-trivial thing will be, instead of pressing enter, you have to say it is shift plus enter. And that's it. So now you learn that. And it's reasonably straightforward. The way it's unlike normal programs, it is the way you think you should be able to type it and it works out. Again, I'm not promoting Mathematica here. I'm just trying to say that it is easy. So I'm encouraging you guys to use it. MATLAB and Mathematica both do a good job, but architecture-wise, Mathematica is significantly different. It is symbolic program instead of a numerical program. So it really works symbolically. It can actually do, in a sense, it can do integers. So, okay, so that's your quiz, and forget this. So, I was going to ask you to plot this itself. So since most of you are not in Mathematica, let's begin with this. Just plot sine function, and if you succeed in this, plot your favorite function. Pick any other function other than sine of x and plot, get something funny or get something rich in there and try to see something that you thought you always wanted to see, and if you try to see it on this. What do you guys use for plotting? Like you all must have plotted, right? There is at the elementary level, there is decimals. That's what I like. You use Python, yeah, perfect. So that's all perfect. So this should be, there's only one line, so it should be easier. The only difference will be there it is database. You generate the data and then you plot the data, right? This is an analytic function. So in a sense, you're giving the function and then plotting. Of course, you can do data also on this, but I am trying to tell you how to do the analytic part. Think of any complicated function and then you can start doing algebra on this. Like if you have a 5-page algebra, you can actually put it in this and do it. Integrals, it can do most of the time. It's reasonably good at doing integrals, like indefinite, definite integrals. Reasonably good. But anyway, so this is all we pretty much solved, right? So for an arbitrary initial condition, we have the solution. That's your harmonic oscillator. But then now we want to build on to this. If you have a harmonic oscillator, let's damp it, right? That's all. At some elementary level, we do it, and then we will put in the force part in there. Any questions at this stage? Comments or questions? Okay. I go back all the way here, and this time I say that's a damping. So we have gravity acting, normal force acting, spring acting, and if it is friction, if you introduce friction from a surface, it is typically mu s times n, the normal force comes in. That's okay, but that's a constant. But that's not the model you want to put. So let's consider a case when this is in a fluid. Like instead of having this on the surface of it, let us keep this as frictionless, but this is all in a fluid, and let me have force of friction. That's just so that I can introduce velocity dependent frictional forces. That's the common damping models that we use in typical harmonic oscillator problem. In this context, it might seem like that is not useful, but it is very useful in most of the second order differential equations or the models that we built. So let the force of friction be equal to minus of v times the velocity. In whatever direction it is moving, it is in the opposite direction it acts. So again, if I were to write the x direction equation for this, so it is mass times acceleration. Mg is in the vertical direction, normal force is in the vertical direction. Spring force is a position dependent force, and the friction force, the damping, right? This is not the friction from the plane. This is a fluid, right? So it is a damping force. It is a velocity dependent force. So it's minus of v times v. So acceleration depends on a position dependent force and a velocity dependent force. divide out by mass again. So this is second derivative of position, and this is equal to minus k over m and minus b over m times v. Oh, sorry, dx times better. Take it out to the left hand side, and this seems to be of the form d over m by t and plus k over m acting on e. If you recall, when you try to find the solutions for this, you get a quadratic equation. So keeping that in mind, you can define your variables appropriately. So let's, like earlier, k over m, that's the same constant that is coming in. So if I were to set the damping to 0, that gives me back my standard oscillator, simple oscillator. And p over m, let me define that to be 2 times gamma. 2 times because the quadratic equations, often when you write it as 2 times that, its roots comes out to be nicer. So that's the only reason why 2 times gamma. So our differential equation is square plus 2 times gamma plus omega square p 0. Okay. Again, set gamma equal to 0, and that's our standard old harmonic oscillator. How do we find the solution for this? So again, I said we start guessing, right? Guessing is the way to go in differential equation. We already know that x of p has sine and cosine as solutions, so maybe, and sine and cosine are exponentials, right? So it's exponential of I, let me say e raised to alpha t is a solution. That's a left, right? Let's check if this is actually a solution. If it is a solution, this should come out to be 0. If I substitute this in here, it should come out to be 0, right? So substitute this in there. If it is a second derivative, I get alpha squared plus 2 gamma alpha plus omega naught squared, and it all gives me back the exponential, right? That's so is that a solution? If this was 0, that is a solution, but if I haven't yet shown that this is equal to 0, because exponential is never equal to 0, right? It is always positive, that's never equal to 0. So if this is 0, then I have shown that exponential of alpha t is 0. So when is this 0? So does it have any zeros at all? So let's look for it. So we have to solve for a simple quadratic equation. So this is a solution if this quadratic equation is satisfied, and alpha was completely arbitrary. So if I choose my alpha accordingly so that that's actually equal to 0, then I'm good. But I can have solution for this after quadratic equation. So alpha is equal to minus 2 gamma plus 4 gamma squared minus 4 omega naught squared divided by 2 times a, right? It's just 2. That's equal to minus gamma times plus gamma square minus omega square. Plus or minus, yeah. That's it. Plus or minus. It's good to see what happens when gamma is equal to 0, because we have solutions for that, right? So if gamma is equal to 0, then alpha is equal to, so that's 0 plus or minus I omega naught. That makes sense, because then there are exponential, right? We already argued that sine functions or exponential functions are allowed. So that seems to suggest that it is good to write this as minus gamma plus or minus I times omega naught square minus gamma square. That way, whenever I set it to 0, that I factor is already available actually. So the solutions could be, so we propose the solution could be x of t. The two linearly independent solutions are defined. So it is exponential of minus gamma plus I t. So this would be a plus, let's say a prime, because a was with sine and cosine. So plus b prime times exponential of minus gamma minus I omega naught square gamma square times c. Both has the same exponential as far as gamma is concerned. So it seems like this is gamma of t times a prime of two oscillatory solutions. Once you reach this state, you say that, oh, I can recognize what is happening. There is a decaying function that you multiply to the standard harmonic oscillator, except the frequency has changed from omega naught square to omega naught square minus gamma square. So you bring back your old solution. So this must be the same as a times sine omega naught square minus gamma square times t plus b times the sine this is just convenient. I don't have to really do this. I'm doing this so that I can match it with my old solution. So how does a damped solution work? So there is a, so properties are that frequency. So switch omega naught to, I introduce the damping in this manner, and the overall solution e raised to minus gamma t multiplied. I change the complete solution or multiply that with a decaying factor, and the frequency itself changes. What would be the unit of gamma here? What are the dimensions of gamma here? Right, it has to be the same as omega naught, right? Because this is squared, this is squared. It's in the square root, it must be the same. So both have the same dimensions. So it is possible that you might think of a situation where this is equal to 0. Like this is, we are constructing a problem, so I can think of a material or a fluid when where it's where the damping is just exactly built in such a way that the spring force and the damping force properties are in such a way that omega naught and gamma are 0 exactly. Okay. In that case, something special happens. This is gone already, sine of 0. Cosine is 1. Right? So it seems like there is only exponential function is the only thing coming out. Right? But then we said that always there should be two functions, correct? We need two functions. If it's a second order differential equation, I should have a and a b. Right? Initial condition for position, initial condition for velocity, that has to be accommodated for. If this is to begin with gone, how will I have my a and b?
Then derive derivation.
Say that again?
Derive x
Derive xt, sorry.
by doing some derivation with respect to p.
Quiz. Okay. So what are the independent functions this is in your homework also? Then and this is called critically damped. If it is over damped, it becomes sine hyperbolic. Right, then there are no oscillatory solutions, there are only decaying solutions. But we will try to think on it. It's kind of a neat. Think of the Wronskian that I talked about. So Wronskian is the key to that, and we will get that. But typically, you don't. It sort of surprises you where it's going. I'll stop here, and next time we will complete this. And in your homework, basically, you work on all these exercises and plotting, and I will start building the green function very soon for this.
Thank you, Dr. Sajas.
See you.
Yeah.